So I was asked to chair this afternoon session. Our first speaker is Maia Vergniory from University of Sherbrooke, and I see that the title is slightly changed. It is Altermagnetism, Classification, Topology, and Non-Relativistic Framework. You have 30 minutes. I will show you when you have 5.
Okay, thank you. All right. Thank you very much. First of all, I would like to thank Jeroen for inviting me to this trip, and the Ukrainian organizers for your warm welcoming and excellent hosting. I hope we can repeat this in more peaceful times, but so far I'm enjoying the workshop very much. So I'm gonna talk about classification, different classification that was given at the beginning of this workshop of altermagnets, how they can display topology, and how we consider non-collinear chiral configuration of the magnetic moments. We can have a very interesting non-relativistic transport signatures. So this is gonna be the outline of the talk. Okay. So actually, I'm gonna run this presentation walking through two different materials. One is the collinear chromium antimonide, where it displays very interesting topological features. And the other one is manganese-3 iridium silicide that we call, in a familiar way, MIRC, that has a non-collinear arrangement of the magnetic moments. And by making this the case of a study, I'm going to show you a different possible classification of altermagnets displaying non-collinear magnetism. Okay, so there has been many introductions to altermagnets, and the way I'm gonna introduce it to you is by using group theory. Till very recent, at least in my group and my collaborators, we were looking either at the 230 space groups, where time reversal symmetry is preserved, or the 1651 magnetic groups, where time reversal symmetry alone is not a symmetry operation of the group. It can be combined with other symmetry operations, but by itself it should be broken. And in these groups, the spin and special transformation are locked. However, recently there is a new group that actually we can use to study materials that has started playing a very important role in the magnetic community. And one way of looking at these spin space groups is by looking at all possible configurations of symmetries of a crystal in this way. So we start with a non-magnetic without the spin-orbit coupling system, like this molecule. The space group is going to be formed by C3. C3 is the symmetry operation that actually turns the atoms. If we now add a spin-orbit coupling, it happens that the symmetry operation is not longer a symmetry of the group, because we also need to turn the spins. So we need to add the operator that turns the spin. And this is how we go from single groups to double groups, or in this case, it's point groups, but also from single space groups to double space group. And then if our system allows for magnetic instabilities and time reversal symmetry is broken, we're gonna have the magnetic double space groups where the spins actually rotate with the C3 symmetry in the same way as the spatial coordinates. So we do this path, but we can do an alternative path by just adding a spin-orbit coupling, by just allowing magnetism, breaking time reversal symmetry, in this case, without a spin-orbit coupling. And what happens here is that we need to add the operator that turns the spin, but the spin and the atomic coordinates are decoupled. So we can, for example, rotate these atoms by 2 pi over 3 and the spins by minus 2 pi over 3. And this is a symmetry of this of the spin space group, but it's not a symmetry of the magnetic double space groups. And these spin space warps have been a case of study in the last years because of altermagnets. However, it's not new. It was already reported in the 70s and the 80s. That was pointed out by previous speakers when they wanted to understand some strange degeneracies in magnets. But it gives way more possibilities than the ones that we have in the magnetic level space groups. So for instance, we'll have 32 crystalline point groups, 122 magnetic point groups, and almost 600 spin groups. Okay, so another way of looking at it, and this is gonna be important in the following slides, because this is what I'm gonna use to describe altermagnetism. This was a slide from your own, actually. If we have a square lattice with a ferromagnetic configuration, ferromagnetic interaction, the Steen's coupling constant are gonna be smaller than 0, and the wave function is invariant under one lattice spacing. Instead, it will have antiferromagnetic interaction, J's are gonna be positive, and the wave function is invariant under lattice spacing times time reversal symmetry, right? So, blah. Now, if we consider the checkerboard lattice that was also introduced in the previous days, and we consider a pure ferromagnetic interaction along the diagonals, it happens that the wave function is invariant under a lattice translation times rotation. And in the very strong limit, what we are gonna have is two sublattices that are decoupled one for the other one. And in our case, the symmetry, and if there are several symmetries, the IRED that is connecting these two sublattices is gonna tell us whether we have an altermagnet or not. And then, of course, this is the band structure of altermagnets. We have the spin splitting of the bands with spin up and spin down connected by translations time, lattice spacing time rotation. And but we still have the Kramers pairs of the antiferromagnets. And again, this table that you have seen already many times, the altermagnets are a new type of magnets because they have a zero net magnetization, but they do have a spin splitting at the same time as a compensated Fermi surface. And we can study them by using spin space groups. Okay, so everything I have presented has been done by other groups. In particular, this was started by Schmeckel, Sinova, and Jowert, but also in the group of Alexander there, they look at this type of magnetism. And for collinear altermagnets, let's say the recipe is given by 3 points. Collinear magnetism in real and reciprocal space. We have a zero net magnetization. And as a consequence, the magnetism in the collinear regime doesn't enlarge the unit cell. Okay, so this was about the introduction. Now let's talk about topology in collinear altermagnets. So there was this inspirational paper by Antonenko collaborators and also by Rafael Fernandez, where they modeled an altermagnets in a Ruthal square lattice and in a 3D case. And what they found is that these two sublattices that are decoupled and that allow for the spin splitting of the spin up and spin down bands also allow for novel topological phenomena, because we can find the crossing of bands of the same spin polarization. So they pointed out that in 2D we can find Dirac crossings, and in 3D we can have nodal lines, and they give some recipes on how can we actually split these bands from a nodal line to a Dirac crossing, etc. But it was not yet reported in a material, and this is when chromium and timonide played an important role. So chromium is an hexagonal, is arranged in an hexagonal space group with a C6 symmetry connecting these spin up as spin down lattices, but also has 4 mirror planes. And we do a DFT calculation. We can see how this symmetry connects the opposite spin sublattices. So this is a proof that actually chromium antimony is an altermagnet. Now we want to look for vials. And we want to look for vials because since altermagnets behave as a ferromagnet, and we know ferromagnets have time reversal symmetry broken, and this allows for many crossings that actually produce vial points. In the same way, an antiferromagnet that has the splitting of the ferromagnet must have many crossings that allow for vial points. What we didn't know is that these vial points have specific properties of the altermagnetic system. So we used two ways of looking for vial points depending on their properties. So the first one was by doing a calculation without the spin-orbit coupling and checking how the different mirror planes were crossing. And then when we allow the spin-orbit coupling, in many systems, in many cases, this caps the vials. And we have a pair of vials connected by a Fermi arc with, but since they have different, they belong to different sublattices, the total SC is equal to 0. However, crossings between the same sublattice are also allowed, why not? And in this particular case, we have same spin vial points that have SC plus minus 1 without the spin-orbit coupling, and this reduces a little bit when we add the spin-orbit coupling, but we found a bunch of them in the Fermi surface, and of course, they are connected by spin-polarized Fermi arcs. So this was a model, and now I'm gonna show you the DFT calculations. So chromium is a metal, and it's, for this reason, is complicated, but still in the band structure, we could resolve different same spin vial points and the connecting Fermi arcs for both terminations. So we have the antimony terminations with these Fermi arcs here and all these vial points, and the chromium terminated surface where we still recognize the same amount of vials with slightly different connecting Fermi arcs. Okay. So this was theory, and now in collaboration with Conley and Oskar Stenberg in Sweden, the idea was to be able to identify them with ARPES. And for that, many measurements were taken and many calculations were done, since, as I said, this is a metal and it's not a van der Waals material, so cleaving is not easy, plus it adds magnetism. So data needs a lot of theory help to be resolved with a good agreement, but I think we succeed. So this is the Fermi surface of the two different terminations. And we can see that we have, in this case, two concentric triangles for each of the surfaces that actually, again, shows the pure altermagnetic nature of chromium antimony. And now we do ARPES calculations, well, no, they do ARPES measurements for different, for the energy, for different energy types. And we found some of them that actually reproduce quite nicely, or as nice as ARPES allows, the Fermi surfaces that were calculated by Mengele. Now, this was for the band structure. Now we want to look if we can identify or resolve the spin splitting. So these are surface measurements for different photon energies, and they did spin resolve energy distribution curves for these two cuts in order to be able to resolve a spin up and a spin down contributions, and somehow they get good agreement also with the DFT calculations. All right, that was for the spin splitting. let's go for the Fermi arcs. And the Fermi arcs, again, we are gonna look for these two here, these Fermi arcs that we have here for both terminations. Well, this is the case of antimony. We did it also for the case of chromium. And we could resolve, they could resolve some signatures of the Fermi arc connecting the valve points, even though, again, it's a complicated material, very difficult to keep. But at least they lie at the same energy and they have the same projection as the calculated band structure. So the last proof to actually see if these are Fermi arcs or not. So valve points come in pairs, and the Fermi arcs are connecting always to valve points. And depending on the cuts, they are gonna be left movers or right movers. So if we consider this loop and we perform the cuts, we see that actually the surface state have a chirality, and this chirality is the ultimate signature of having a Fermi arc in a material. So with these three, with these three proofs of ARPES data and DFT calculations, we reproduce the Fermi surfaces, the spin splitting, and in our opinion, there is enough evidence to consider the surface state Fermi arcs. We can conclude that chromium antimony is an altermagnet with a specific altermagnetic topological bias. And this was calculations performed by Mengli, where she shows that actually Fermi surfaces and Fermi arcs connecting different bands have a specific spin polarization. Okay, so now we are gonna left behind the collinear altermagnets, and we're gonna go for non-collinear altermagnets in chiral crystals. And first, I want to show you that these chiral crystals, in a few slides, are being a case of study because they are very interesting. So we call them chiral, but they belong to the Schonk space groups, which means that they have no improper symmetries. It's a pure rotational crystalline structure. So they can come in two different configurations because the mirrors they cannot superimpose, but they can have the same crystal structure with a different LCP. If I want an enantiomer, we call, and I apply inversion of mirror, I get the other enantiomer, which is its mirror image. So these are the D20 compounds, and I've been studying them for quite some years. They have also very interesting properties because they have valve points. Of course, inversion is broken, so it allows to have many crossings, and these crossings can carry a topological charge. And depending on the enantiomer, the topological charge is positive or negative. So they are really mirror images in terms of topology. And then they have Fermi arcs, which are the surface state connecting the two vials. And again, depending on the enantiomer, the chirality at the surface is different. It can go in this diagonal or in this other diagonal. Plus, they can hold these chiral crystals because they have non-symmetric. They can have non-symmetric symmetries. There is band folding, and this band folding actually adds the Chern number, so we can have higher Chern numbers, like corresponding to, in the case of the 3-fold spin 1, to the 6-fold double spin 1, and to the 4-fold to the Rarita Swinger firm. So it has interesting quasi-particle at their nodes. And we did ARPES calculations again to prove, because they were predicted theoretically. So then we did what Niels Schroeder did ARPES measurements, and he could see here we can resolve the Fermi arc that actually goes from R through gamma to the other R point, and depending on the sign of the Chern number, they have one chirality or the other one. So by looking again at the right moving modes or the left moving modes, by looking at the ARPES data, we can actually predict what is the the sign of the Chern number of this Fermi arc, and in this case, it was positive. And then in a more sophisticated arc-based measurement, the group of NILs could also resolve the spin splitting, because with larger numbers we'll have double Fermi arcs, and thus this spin splitting proved this double Fermi arc. So this was the first experimental observation of a maximal Chern number 4 in a material. But they are also interesting because since inversion is broken, we can have orbital angular momentum along the whole region zone, and by performing a circular dichroism measurement, again, Niels, in collaboration with us, he could resolve the orbital angular momentum spin texture, and it behaves like a monopole. And they have interesting and very high orbital Hall conductivity contributions that can swap their sign depending on the nantoisomer that we are putting between the crystals. And lastly, they also have a very interesting spin texture. So we have different spin texture, like the orthogonal locking, the mixed locking, and the parallel locking. And in particular, these materials add to these possible spin textures a new one. So if we look at the spin texture of the double Fermi arcs, which come from a Hedgehog bulk spin texture, when we projected it on the surface, we'll have a spin momentum locking along almost the whole Brian zone. That again was also measured in collaboration with a group of NILs. This is the spin up and the spin down, and this is coming out from gamma, and this is the spin momentum locking coming on from R. So this family of materials are very interesting. Okay, so this family of materials are very interesting, and in particular, okay. In particular, we were looking for high order topological nodes in magnetic materials in this work in 2019. And manganese iridium silicide came up as one pure non-collinear magnetic crystal, which means that only time reversal symmetry is broken. The rest of the symmetries are preserved because the magnetic moments follow the bonds of the atoms. So this was the magnetic realization by different groups of the V20 compounds that I have been studying for several years. So the band structure without magnetism has this six-fold crossing, these double spin bands with a large Chern number. When we break time reversal symmetry, these are Cram spurs that split, but we still have these three-fold crossings at R, and these two-fold crossings at the gamma point that carry also a Chern number. But anyway, this goes to 2019, but still, when people start talking about altermagnets, somehow this magnetic configuration lie in the original description of collinear magnets, which is like time reversal symmetry is broken and it doesn't exist in combination with any other symmetry. It has sublattices in a complex way, and it doesn't enhance the unit cell. So just like that, we cannot claim anything, but in collaboration with Paul, we try to apply his Landau theory to see if we could find all the parameters that could point into an altermagnetic behavior. So for noncollinear altermagnets, he already introduced it yesterday. The two sublattices not related by inversion or translation must be related by a non-trivial irrep in one dimension called gamma, and this is what we add to the Landau theory, as he said yesterday. to the Landau equations. We could do a generalization to noncollinear altermagnets in this following way. So bands no longer carry a global spin quantum number, so the lattice is not longer restricted to a one-dimensional error. And because it's a noncollinear crystal, it breaks C2T, so it allows for real space part of multipolar order that can be odd. And the consequences are we have non-trivial spin texture and novel spin transport signature in altermagnets. So this work was done by Mengli Hugh at Leibniz Institute, and she did a full group theory analysis of our crystal. So symmetries allow for band splitting even without the spinor recoupling. So it's because it's an antiferromagnet, and it's an antiferromagnet with wave vector 0. And we have 12 atoms in the unit cell with noncollinear local magnetic moments. And we have a two-dimensional tetrahedral point group that splits in 3 reps. And by doing a symmetry analysis, it happens that the constraints allow only for the irrep T to exist that has an order parameter associated that we can introduce in the Landau theory. So these are the different spin sublattices that I was talking about. It's, as I said, it's more complicated, but these are these triangles formed by the magnetic atoms, and the irrep actually connects the different sublattices. So it's complex, so it's not directly connected to the magnetic moment, but it allows for spatial and quadruple terms, like this one that gives rise to the hedgehog spin configuration, or the quadruple one that gives rise to this spin locking. Okay. Now, mainly develop a Kondo lifetime binding Hamiltonian to see, because all that I have said till now has been developed derived by symmetry, and now we want to see if we can actually find it in a crystal. So the first approximation was this tight binding Hamiltonian, where she reproduced the main features of the band structure, which are the dimension of the irreps at the high symmetry points and the connectivity of the EBRs. And she found that in this tight binding Hamiltonian, she could see the hedgehog spin structure and the quadruple one. And then she did first principle calculations. This is the band structure. According to DFT, is metallic. It could be that it has, when we add correlations, it might gap, but still by doping it, we can recover bands at the Fermi level. And doing DFT calculations, you could actually reproduce the phenomenological features that she predicted in the model. And this is the last slide. So she will check for non-zero terms of the spin Hall tensor and the Edelstein effect, and she saw that actually we can have contributions to the spin Hall and Edelstein effect even without the presence of a spinor recoupling. And with this, I conclude the talk. So chromium antimonad, we have observed the altermagnetic splitting, valence and Fermi arcs. They can carry topological charts with finite spin projection. And these properties derive from the combination of symmetry and topology, which is a characteristic of bias in altermagnets. And using, for the Mirci, using Landau theory, we agree that it can predict altermagnets. We have predicted a noncollinear chiral altermagnets. The spin texture is more integrate. It has a momentum space spin texture that comes from the complex magnetic configuration. And large spin Hall and Edelstein effect coexist, showing with spinor recoupling the dependence. And this can be applied to other non-material of the same chiral systems. And with this, I thank mainly Oleg, Jeroen, and Paul, and all the funding agencies, and you for your attention.
So let's thank the speaker. And I believe that we have time for one brief question.
Online, just one question.
Oh, there is a question online, so please.
Hi. Is my turn or I'm not sure?
Yes, you're here.
Okay, yeah. So can you maybe show when you mentioned, because I wanted to correct a few things, some things that seem to be confused from before. When you introduced this notion of altermagnets, this first two slides that you showed, can you put it back if you have a chance? So the beginning, I'm sorry for that. Because it's important, I think. Yeah, there. For some example, there, that first slide, there was a slide before that, yeah. So one thing that is, no, don't move it there. So what I think is important to say in there that I thought I was clear a bit in my talk, whereas the first three lines are correct, yeah, of course, but when they look for the delimitation between the phases, is all in spin groups that we're looking at essentially exchange symmetries delimiting the phases, and the spin orbit coupling afterwards can, depending on the magnetic space group, for applying for all three will give you some different responses. But MSG and MSCD is not defining the phase, because I've illustrated that, for example, M prime, M prime, M will be, in fact, a ferromagnet, antiferromagnet, and altermagnet. You can have them all. So essentially, it is only spin space groups that are delimiting these phases clearly. This is why you should, that's the part that define altermagnets, because otherwise it's not real, that it's not true that MSG and MSG is defining ferromagnet, antiferromagnet. The MSG's magnetic space groups do not do that by definition, because we have examples of it, right? And then in the other slide, when you mentioned this, because I wanted to correct the continuous. I thought it was not. The previous one, maybe. Sorry. Yeah. So with the Young paper that a lot of puzzles that is continually discussed, because it's a paper that has many wrong things. There's not a single statement there other than Zener's Kramer's theorem is broken, and then you do the calculation. There's not a statement there about any sort of even polarizations, spin groups that actually delimit in the systems. And in fact, many of these spin splittings were done a few papers before. So if you're going to put references, it put to the other ones. And in fact, that paper predicts that P-wave magnetism does not exist, which is actually wrong. So that's one thing that I'm always careful when I see this there connected to altermagnets, because in fact, they were criticizing and do not understand altermagnets there. So that's not really the definition.
But that we can discuss it with Alex, because if I don't put it and it's in the audience, I get the opposite message. So
well, good for him, but at the same time, you can also tell him that why he's wrong. I mean, it is not about the fact that you have a guy that is angry. I can tell you. Yeah. Okay. That's not how we should work. Yeah. Science doesn't work that way. It's not about who is the angriest one, I think. Yeah.
Okay. Thank you. Yeah, I'll take all that into account. Thanks.
Okay. I'm sorry, we are 10 minutes out of schedule, so let's send the speaker and we should continue.